So I think we have a very fascinating and a very timely topic today, which is this deep subsurface access for icy worlds. And I think everybody realizes that when we say icy worlds, what we really mean is ocean worlds. And what we are primarily interested with on these worlds is, of course, the deep water bodies, the deep oceans that are present on them. Landing on the surface is great and is a necessary precursor for our ultimate goal, that ultimate goal being directly accessing those oceans. The great challenge there being their depth, which is anywhere from hundreds of meters to 100 kilometers. So the purpose of the workshop this week is to begin tackling the technical challenges of that. But as the short courses this morning show, you can't tackle a technical challenge without understanding the basic science that you also have to deal with. So the four talks this morning will deal with all those challenges from the scientific to the technical. Will give us a bit of an overview on efforts that have been undertaken in the recent past or are currently active on Earth to overcome the challenge that we face on Earth in this area as well. So our first speaker will be Dr. Christophe Sotin from JPL.
Well, thanks everyone for coming here. Actually, this workshop started a few months ago. I think Kurt said a few words saying, you know, it would be time now to be serious about accessing the subsurface ocean of icy worlds. And he asked us to bring together people from with different expertise in order to look at this problem. And so the committee, not the committee, but the leaders, we are trying to get people from planetary science, from people who drill in different places, including the Arctic ice, people who know about the ice properties, because from discussion I had with the engineers, I found out that it's very important to know, for example, the temperature profile, what will be the bulk modulus of the ice, how it varies with grain size, you know, all these things that we have been studying for different icy worlds. Having people who can do models, I think it's important too, because we need to put as much as the complexities that we know about the ice into those models in order to make some prediction. People who can do some mission design and people who are astrobiologists. I mean, bring all these people. And then you have a group of 30 persons. And then you have to pick. And I know that we couldn't pick everyone who has the expertise in these domains. But I think it's a first step. It's a very challenging one. And I'm very happy actually to be part of that project. Just as an aside, I was born. I grew up with reading Jules Verne, because I was born in the same city. Jules Verne was born, and he invented things that we didn't think about, and we didn't think at that time that it would be possible to do it, because there were some technologies that he didn't know about, but eventually they become available. So somehow this kind of challenge. Drilling through kilometers of ice on an icy world, that seems really remote, but when you think about it, I'm pretty sure it's something we can achieve in a reasonable future. Of course, what we want to look at, actually I have a pointer here, is to look at places like Europa, where we think that there may be some hydrothermal vents, and I won't go now into the details, but the idea is to find life, to ask the question whether life can exist in these environments. And I just took that from another proposal where you need energy, you need some building blocks, you need liquid water, you need different conditions. And also something that I find very interesting is that at the same time we are exploring these new worlds, we're also exploring the ocean, the terrestrial ocean, and we're making discoveries about the terrestrial oceans, about life at the interface between rocks and water. And at the same time also, we are studying early Earth, and we are going back 3 billion years ago when the first organisms started on Earth, when we had this big event about the oxidation of the atmosphere on Earth. And we are trying to understand how life started on Earth, and looking at other places I think is very fascinating as well. So my first talk is going to be on Earth, Europa, and Enceladus, ocean rock interaction and prospects for life. And I know that in this group there are people like Chris Germans. They know much more about serpentinization, hydrothermal vents, that than me. But don't hesitate to comment, to ask questions, to tell me you are completely wrong. So we are living in a very exciting time. I think this question about life somewhere else in the universe is maybe the most important question in planetary science. And at the same time, we are discovering extrasolar habitable planets. And I just took this plot from a recent paper by Fulton et al., which shows that you have two peaks, one peak at terrestrial planets, Earth-like planets, and another peak which is closer to the ice giants. And you are asking questions about whether ocean planets can also exist, but this is very remote. We won't get a lot of information on these exoplanets, but it's telling us something about the prospect for life somewhere else in the universe. But at the same time, we're asking the question about oceans in these icy moons. And once again, I took this image from the Europa SDT, the Europa Lander SDT, which, by the way, is a very good reading. I don't know if you have had the chance to read this science definition team report, but you learn a lot about about how you can expect life on Europa. And so the idea is that maybe at the bottom of the ocean, as I will explain later, there may be conditions very similar to what we know on the terrestrial seafloor. And maybe you have hydrothermal vents. And there is one theory that says that maybe life started in this kind of environment. So it's very debated, but you can see that the other way around. You can say, well, maybe if life didn't start this way, by looking at these places, we may find the answer. Okay, ocean worlds. There are a lot of ocean worlds. The Galileo mission found water in these three icy moons, Galilean moons, Callisto, Ganymede, and Europa. And then Cassini discovered that there is also deep oceans on Enceladus and Titan. And there are also studies about Triton. These ocean worlds could exist, which means that you can still have water at depths in different places in the solar system. And of course, one ocean world that we know about is the Earth. And you can think also of old oceans on Mars, maybe Venus. Who knows what Venus looked like 4 billion years ago. And I forgot to add Ceres, but I think from the Dawn mission, there is good evidence that Ceres had some ocean in the past, and it may be frozen now. Okay, so what about habitability? Very often, the Mars program started with follow the water for habitability, but you have more than just the water. So water has been found in different places. So once again, Callisto, Ganymede, Europa, Enceladus, and Titan. And then in terms of habitability, you can add organic material. So we know that there is a lot of organic material on Titan. And then on Surdas, as I will show you, with the geysers that come out, there is the ocean coming out, and there is good evidences that there is some hydrothermal activity at the rock-water interface on Enceladus. So the way I think I'm going to speak first about Enceladus, because we have a lot of data about Enceladus, and then I will say a few words about hydrothermalism, serpentinization, and then we will go to Europa, and I think that will be the next talk by Louise Proctor. I put some numbers because for the study we will need to have some numbers. I talked about energy, how much water, size may be important too. So I compare the Earth. I put Io because, as you will see, tidal heating is very important, and the best example we have in the solar system of tidal heating is Io. Just to give you an idea here, the amount of power which is generated by tidal heating on Io is 100 terawatt, which is more than twice what is extracted from the Earth. You have 42 terawatt coming out of the Earth, which gives a heat flux of 75 milliwatt per square meters. On Io, you get 2 watt per square meter just by tidal heating. So in terms of the amount of power that you have by tidal heating can be quite large. This is Titan, so it's you can see that it is much less. This is a gigawatt. On Europa, still depending on calculations, you get something like 1 terawatt. And on Enceladus, you get 6 gigawatt, which doesn't seem a lot, but bear in mind that Enceladus is very small, only 250 kilometers. And that's where nature is great too. Before Cassini, no one expected that Enceladus would be so dynamic. I mean, a small body, 250 kilometers in a very cold environment, should be frozen. It's not. It's very active. It has geysers. There is a lot of activity. Other numbers are the density, from which you can extract the mass of water compared to the mass of silicates. On Earth, actually, the amount of water is pretty small, on the order of 210 to minus 4, the total mass. On the other bodies, like Titan, it's closer to 50%. On Enceladus, it's much less. I think the values. I think we have 5 times the amount of oceans on the Earth on Europa. Sorry, this is Europa. And on Enceladus, it's about 1 Earth ocean that may be liquid in Enceladus. And I have some other numbers, but just I think it's important to realize that we can go from very small bodies like Enceladus to much bigger one like Europa, 1,500 kilometers, and Titan. And gravity is going to be very different, which means that stresses, the way stress increases with depth, is going also to be very different on Enceladus and on Europa, for example, if you want to compare both of them. Okay, so the case for Enceladus. Cassini discovered a global ocean on Enceladus. I won't go into the details, but it was by measuring the libration of Enceladus that a paper demonstrated that a paper led by Peter Thomas demonstrated that the ice crust has to be decoupled from the interior. Then the plumes were discovered, and Cassini went through the plumes, detected salts, some ocean grains, organic molecules, and evidence for hydrothermal activity at the ocean's base, like, for example, the presence of, the nano grains of silica were found in the E-ring of Saturn. But the E-ring of Saturn is thought to come from Enceladus, so that's why we think that they come from Enceladus. And that's the kind of stuff you can find at hydrothermal vents. So the question then was, how can you get so much activity on Enceladus? Recent studies looking at the topography, the gravity coefficients. We have the degree 2 gravity coefficient on Enceladus, and also looking at the stresses. Found out that actually the thickness on Enceladus can vary quite a lot. On the south pole, it can be as low as 6 kilometers. On the North Pole would be on the order of 10 kilometers. The average would be 20 kilometers. But at the equator, you can get values as high as 40 kilometers. So there were 2 studies, one by Keck et al. 2016 and Boite et al. 2016. So you get map of the thickness of the ice crust on Enceladus. And it's not constant, it's clear, it varies a lot. So if you want to drill somewhere on Enceladus, I guess the people, the engineers, would like to go where the thickness is lowest. So you go to the South Pole. Unless you like challenges and go to the to where it's thicker. What was the and also by knowing the thickness of the ice crust. And by assuming that the temperature at the interface between the ice and the ocean is the melting temperature of water, then you can deduce the total amount of heat which has to be extracted through the crust. So this is done in this paper. And they find out that you need between 15 and 20 gigawatts in order to have such a crustal thickness. Yes?
So, quick question. Why is it the opposite that you would expect? Why is it thickest in the equator and not in the poles?
Well, it's tidal heating. Yes, yeah, I haven't shown. That's why I was thinking about it, because I have another slide where we did tidal heating calculations on Enceladus, and we found out that you have much more tidal heating at the poles than you have at the equator. But then it's. I mean, the question is, I'm not sure it's fully solved, because then the heat has to go through the ocean, and how it is redistributed into the ocean, and how it goes to then to the crust. I'm not sure it's fully understood. But you know, that's the image you get when you look at the topography and you look at the gravity coefficient, and then you infer the thickness of the ice. Yeah, so the total amount of heat that you need is something between 15 and 20 gigawatts. And at the beginning of the Cassini mission, we focused on where the geysers are, you know, where you have the tiger stripes and you have the geysers coming out. And we found out, we measured the amount of heat which comes out with a SIRS, infrared instrument. And we found out that it was 6 gigawatt. So you have the 6 gigawatt at the South Pole, and all together with the thickness of the ice, and by making this assumption about the temperature at the ice-water interface, you find out that you need 20 gigawatt altogether. How do you produce 20 gigawatt on Enceladus? It's clear you cannot produce that with radiogenic decay. There is not enough silicates, enough radioactive elements to produce this amount. So it has to be tidal heating. It has been a struggle for a lot of time to determine how we can get this amount of water. Some other observation by INMS on Cassini, they found CO2, but I think, you know, something which was very important and very much discussed is H2, hydrogen. And the reason why is that hydrogen is a produce of alteration of rocks, silicates by water. Right? It's what we call serpentinization, which produces hydrogen. And then by finding this hydrogen between 0.4 and 1.4% of H2 in the paper led by Hunter Waite, then you can make some prediction on how much hydrothermal activity you have on Enceladus. So you know that was the paper in 2007, and we call that serpentinization. If I come back on that, so once we have that, the question we were asking, it was a paper by Roberts in 2015, is that actually the pressure on Enceladus, inside Enceladus, you know, in the center of Enceladus, it's only 60 or 80 MPa. It's very, very small. So actually, when you think about silicates, when you go to the lab and you do lab experiments and you sinter the powder, you find out that you need, in order to get something without any porosity, you need to apply much higher pressure. So the idea came, and it was in this paper by Roberts in 2015, that actually Enceladus would be fluffy. You know, the core of Enceladus would be fluffy, that there should be a lot of porosity. And by the way, when you look at the gravity measurements, you find out, looking at the moment of inertia and the mass, that actually you can get porosity as large as 20 to 25%. And actually, the 20% is if you take the density of hydrated silicates, which is much less than the density of non-hydrated silicates like olivine or pyroxenes. So if you take olivine and pyroxene, you find a porosity even larger. So in Roberts et al., what they had is a mixture of rock and ice. But the question is, if you have water and hydrothermal activity, how the water is going to circulate, to percolate into this silicates, these very porous silicates, and how much tidal heating is going to appear in this kind of aggregates. And actually, the viscosity of aggregates is not very well known. And with in a paper from which is coming out, led by Gaël Choblet, and it's coming out in Nature Astronomy. Sorry for my French. So Nature Astronomy this year, we find out that you can produce as much as 25 to 50 gigawatts just by the deformation of these aggregates into the center of Enceladus. So somehow it changed the vision that we had about where is tidal heating distributed on Enceladus. At some point we thought that most of the tidal heating was at the interface between the ice and the ocean, because the ice has a viscosity which is pretty low and you can have quite a lot of tidal heating. But now on Enceladus, because of the very small gravity, because of the small size of the body, the deformation of aggregates can actually produce this amount of tidal dissipation. And then we solve the question. Julie.
Yeah, I wanted to mention that on Surdas,
Mm-hmm.
we also found a density of 2.4 1 per cubic centimeter for the core, which we also interpret as evidence for porosity.
Yeah.
And since the gravity regime is similar, it supports this model.
Yeah. Well, good. We haven't yet applied that to Cirrus, but yeah, we should. But the pressure are much higher on Cirrus. I guess in the center you must get to 800 or.
At the center it's 140 megapascals.
100. Okay. Yeah.
But at the outer
Okay.
layer of the core, it's going to be
Yeah.
similar.
And so when we presented this work, of course, the question was, can this apply to Europa? I mean, that would be great. But Europa is too big. You know, the pressure on Europa are much larger. So it's. I was going to say it's unclear. Right now, I think that you cannot produce as much tidal heating in the Europa's core or Europa's silicates by this process, because it's not going to be an aggregate. And something I forgot to mention is that when you do the calculations, so it's a 3D spherical calculations of water percolating into the rocks. We find out that the whole ocean of Enceladus would be processed in tens to hundreds of million years. And then you go, and I spoke with my friends who do geology on the terrestrial seafloor, and I said, how much, I remember, you know, when I was taking a class looking at serpentinites and all these hydrated rocks under a microscope, how much of the rock is actually hydrated. It's never 100%. You still find pyroxenes, you still find, I can see Chris who says, yes, okay, great, I got this right. But I am wondering, what is, do we have any evidence on how much time does it take for silicates to be hydrated, to turn into serpentinite? And I think that would be, even for the Earth, apparently it's not very well known. Okay, so I think that's pretty much what I can do. If you take, so this comes from a paper by Andreani et al. 2007. So she studies the terrestrial seafloor, and she takes this kind of expression for olivine. So you have 75% of magnesium and 25% of iron. And this case is nice because you produce 1 molecule of H2 for 7 molecules of H2O. And then the way you get the H2 is because you have the oxidation of iron, which goes from 2+ into the olivine to 3+ into the magnetite. And so when you look at the numbers for the Earth, and I did some, I look at some papers, you get something which is on the order of 0.5 terawatt for the serpentization of the terrestrial seafloor. And I took the Atlantic, and I can't remember if I also included the Pacific, because something that I learned is that serpentization on the Atlantic is very different from serpentization on the Pacific, and I also need to understand why. But anyway, it's not negligible, you know, it's 1% of the total flux which comes out of the Earth. So serpentinization can be a great way to produce heat too. And the water can percolate down to 4 to 10 kilometers. That's, I mean, there are several papers who have looked at how deep the water can percolate. And so the pressure, that's something we have to keep in mind, is on the order of 100 to 300 MPa here on the Earth. And maybe this is also relevant to Europa, because when we look at the ocean silicates interface on Europa, depending on the pressure, you may have some idea of how deep the water can interact with a rock. Yeah, some more, but I'm just going to move. Now I go to Europa. So as I said before, Galileo has discovered the global interior ocean. The moment of inertia inferred by the gravity measurements. And we have to keep in mind that Galileo was not as good as Cassini for gravity measurements. For example, we have 2°2 gravity coefficients that we call J2 and C22. And for Galileo, it was assumed when we inverted the observations that J2 was 1/10 of C22. So we did not invert these two gravity coefficients independently from each other, which does not allow us to say something about how what is the hydrostatic state of Europa. With Cassini, for both Titan and Enceladus, we are able to invert the coefficients independently from each other. So it's much better known for Titan and Enceladus whether they are in hydrostatic equilibrium or not compared to Europa. So we have to take, the Europa Clipper is going to give us some more, of course, more information, so that will be quite important. But I want to stress that for Europa right now, we still have this assumption about hydrostatic equilibrium, which may not exist on Europa. And we know on Enceladus it does not, for example. So from this, assuming that it's hydrostatic equilibrium, then Europa would be fully differentiated, and models where you have even an iron core, a silicate mantle, an ocean, and ice crust. These models are consistent with the mass and the moment of inertia that we know for Europa. Models that have been developed since the Galileo mission suggest that tidal dissipation is mostly located at the ice-ocean interface because that's where the viscosity is low enough to produce a lot of tidal heating. Other papers have looked at how much tidal heating you can have on faults because during the eccentric orbit of Europa around Jupiter, then you're going to have some shear stresses, so you may create some water. You have to tell you that it's pretty difficult actually to create water, to melt the ice along the faults. But you can turn the knobs and you can find some parameters that work. And then there were studies about the thickness, and this comes from Bill McKinnon's paper in the ICE-1 layer. You go from, if the thickness, shell thickness is thin, less than 20 kilometers, you are in a domain where heat is transferred by conduction. If it's thicker, then convection will start. And so by conduction, it does not depend on viscosity. By convection, it depends on viscosity. You can see the numbers that we have in terms of heat flux between 5 milliwatt per square meters to 30 milliwatt per square meters, depending on the shell thickness. So we have some ideas, and we have some models. In terms of determining the temperature profile in Europa, depending whether you believe in a conductive model or a convection model, we can produce temperature profiles. What's really great about Europa, and that I learned from Kevin and other people, is that you have a lot of interaction with Jupiter and with energetic electrons, and so it can create some oxidants on the surface of Europa. And I think what we need about, and this comes, by the way, also it's an image from the Europa lander SDT, and a credit to Theolis et al. 2017. But what I learned also about life is that you need to have some differences in redox, differences in pH. So you need to have an environment where it's reduced and an environment where it is oxidized. And Europa is great because you can find the oxidants on the surface. And you have the reduced stuff in the interior. Kevin, tell me if I am wrong, or Chris, no, okay. So far, so good. Okay, I can see that I still have 2 minutes. Tidal heating, we can do some calculations. I have the numbers, we can discuss that during the workshop. It's quite interesting to find out that if you apply so for IO, we have the values. So for IO, it's great. And then you can scale Europa to IO. And when you do that, what you find out is that the heat flux at the ocean silicate interface is 82 milliwatt per square meters. So don't believe the 2, of course. It's more like between 60 and 100 milliwatt per square meters. But what is interesting is that it's quite comparable with the value we have for the Earth on the terrestrial seafloor. On Surdas, if you do the same kind of calculations, and I haven't look back at these calculations with the new findings about tidal dissipation in the core, the value was much less. But I think I have to revise this number, so sorry, it's not up to date. Okay, something I like to point out is temperature pressure plot. So I put the H2O phase diagram. You have the triple point of water here, a critical point of water, which is at 650 Kelvin. And at this pressure, which is about a few tenths of MPa. What I have in red, so the liquid is between, of course, the solid and the gas, so it's this domain here. In red is the Earth, so I just put the temperature profile in the Earth. It's a log scale, so that's why it looks kind of weird. This is the temperature profile on Europa. So here you are on in the ice crust of Europa, and then the pressure increases. At some point, you're going to cross the melting point. So this is a place where you have the ocean, and here you have the silicates. And then you can see that if you plot some kind of temperature profile inside Europa, you find conditions which are quite similar to what we have on Earth too. Now, if you look at Enceladus, so the same thing, it's very cold at the surface, so you have the temperature that increases with depth. At some point, you cross the melting point, then you have the ocean here, here is the silicates, and then you increase the temperature, and you are barely at the critical point. And I don't know if that is important or not for hydrothermal activity, but there may be some kind of minimum size in order to be at higher pressures than the pressure for the critical point in order to get all this circulation. Because otherwise what's going to happen is that the liquid is going to transform into gas, and then you will have a lot of volcanic activity or geysers going on Enceladus. Okay, so now is my summary and conclusions. I have 1 second. A lot of ocean worlds have been discovered in the last 30 years, and the question is whether life is present in these oceans. Enceladus and Europa are likely to have an ocean in contact with a rock, which makes them more interesting, for example, than Ganymede or a Titan. Also for Titan, it may be the case that the ocean is in contact with a rocky core as well, and actually it was in contact in the past. Cassini demonstrated that hydrogen, a product of serpentinization, is indeed present inside Enceladus and is released into space. Such processes may exist inside Europa, still open question, and exploring extraterrestrial oceans will provide the answer to the presence of life. Well, an answer, I guess I shouldn't put the answer. And need to know the characteristics of the ice crust to investigate the potential of drilling through it. And I think that's what I try to do with all these numbers. Thank you very much.